All right, let's talk about something we all take for granted, bridges, specifically the invisible shields that protects them. There's this constant, unseen battle going on to keep these massive structures from falling apart. So what's the secret? Well, that's what we're going to dive into. I mean, have you ever really stopped to think about it? You're driving over a bridge and you just trust it. You see all that steel, all that concrete, and it feels solid. But what you don't see is this relentless attack from the environment, just trying to break it all down. So what's stopping it? What's the secret defense? And here's the kicker. The answer isn't some big, obvious thing. It's not another layer of concrete or a thick coat of paint. Nope. The shield is totally invisible, and it actually works inside the concrete. So to really get what's going on, we've got to zoom way, way in. Okay, so first things first. Before we can talk about the solution, we have to understand the problem. And the problem, well, it starts with the very nature of concrete. Yeah, I know. Concrete looks completely solid, right? Like a rock. But if you had a super-powered microscope, you'd see something totally different. It's actually more like a really, really hard sponge. It's just full of these tiny little holes and channels. We're talking microcracks, pores, you name it. And just look at this. This picture says it all. That is not a smooth, solid surface. It's a whole network of little pathways, basically just rolling out the welcome mat for all sorts of bad stuff. So what kind of trouble are we really talking about here? Okay, meet the enemies of concrete. You've got water, which is a big one. It seeps in, then in the winter, it freezes, expands, and boom, you get cracks. Then you've got de-icing salts. We need them for safe roads, but they carry these nasty little chloride ions that get inside and just eat away at the steel rebar. It's like a cancer destroying the bridge from the inside out. It's this quiet, relentless attack that's happening all the time. So, the big question is, how in the world do you fight an enemy that's so small it can sneak through microscopic holes? Well, the answer is pretty elegant. You fight microscopic with microscopic. And this is our hero, the penetrating sealant. Now, this is not paint. Paint just sits on the surface, right? This stuff is different. It's a liquid that literally dives into the concrete's pores. And that's the key. It works from the inside out. The surface looks exactly the same, but on the chemical level, everything has changed. So, there are basically two main ways these sealants work. On the left, you've got what are called water repellents. Think of these as giving the inside of every single one of those tiny pores a microscopic raincoat. It makes the concrete hydrophobic, which is just a fancy way of saying it hates water. Then on the right, you have pore blockers. Their strategy is a little more straightforward. They just get in there and plug up the holes completely. Both can work, but they're very different approaches. Okay, so how does this actually work? How do you make concrete hate water? Well, it all comes down to some really clever chemistry. And here you can see the difference, clear as day. On the left, you've got untreated concrete. Water hits it, and it just soaks right in. But look at the right. After it's been treated, the water just beads up, sitting on the surface. It can't get in. It's like the concrete is actively pushing it away. So, what's the magic behind that? Let's break down how one of the most common types, called silanes, works. It's basically a four-step chemical dance. First, these super tiny silane molecules are literally sucked into the concrete's pores, a process called capillary action. Then, here's the cool part. They find moisture that's already inside the concrete and use it to kick off a chemical reaction. That reaction lets them grab onto the walls of the pores and bond with them permanently. The end result? That durable water repellent layer we were talking about. It's not just a plug, it's a fundamental, permanent change to the concrete itself. All right, so this science is awesome, right? But what does this actually look like in practice? How do engineers take this chemistry and apply it to protect these huge, expensive bridges we rely on? Well, it turns out there isn't just one magic bullet. Engineers have a whole menu of options to choose from. As you can see here, epoxy sealers are actually the most common, but right behind them are the silanes we just discussed, followed by acrylics. What they choose really depends on a ton of factors: the type of bridge, the local climate, how much traffic it gets. But there's a catch. It's not always so easy. And here's one of the biggest challenges they face in the real world. The concrete we use for bridges today is super, super dense. That's great for strength, obviously, but it makes it incredibly difficult for these sealants to soak in deep enough. This quote from a Western Michigan University report says it all. They found they were only getting about 4 millimeters of penetration when the minimum they really needed was 6. That's a big problem. So, this whole penetration challenge has actually led to two different schools of thought on how to best protect bridges. Here in North America, the strategy is often to rely on a single, really strong layer of protection, like an epoxy overlay or just the penetrating sealant on its own. But over in Europe, they tend to think differently. They often go for a multi-layer system, a whole defense in depth approach, where the sealant is just one important piece of the puzzle. And this is a perfect example of that European approach. It's like a lasagna of protection. You start with the concrete deck itself at the bottom, then you add an epoxy primer, then your sealing layer, then another protective layer, and only then do you put the asphalt driving surface on top. The sealant is still absolutely critical, but it's not working alone. It's part of a team. Okay, so we've gone super deep, from the microscopic world of molecules all the way up to global engineering strategies. But let's bring it back. Why should you care about any of this? Why do the guts of a bridge matter? Honestly, it all boils down to this one number, 1/4 of an inch. That's about 6 millimeters. If the sealant can get that deep into the concrete, it creates a protective zone that's tough enough to withstand traffic wearing down the surface and the sun's UV rays trying to break it down. It is the magic number for making sure this protection lasts for a really, really long time. And when we hit that magic number, the payoff is huge. I mean, first, the bridges themselves last longer, which is pretty important for public safety, right? It also prevents the kind of major damage that leads to those massive, soul-crushing repair projects that shut down lanes for months. And get this, studies have shown that for every single dollar we spend on this kind of preservation, we save up to $6 in future repair costs. So yeah, this tiny, invisible shield ends up saving us, the taxpayers, a ton of money and a whole lot of headaches. So, the next time you're driving across a bridge, maybe you'll think about it a little differently. Will you think about that incredible, invisible science holding it all together? This amazing fusion of chemistry and engineering winning a hidden battle every single day, right there beneath your tires. It's all happening, one molecule